March 2025, day 7. Laboratories. You thank the cephalopods for the help and exit the trash compactor, finding yourself in the familiar halls of the North Pole Research Wing. Based on the large sign that says Teleporter Hub, they seem to be researching teleportation. You can't help but try it for yourself and step into a large yellow teleporter pad. Suddenly you find yourself in an unfamiliar room. No doors. The only way out is the teleporter. Unfortunately, the teleporter seems to be leaking magic smoke. Since this is a teleporter lab, there are lots of spare parts, manuals, and diagnostic equipment lying around. After connecting one of the diagnostic tools, it helpfully displays error code OHNO, which apparently means that there is an issue one of the tachyon manifolds. You quickly locate a diagram of the tachyon manifold. A tachyon beam enters the manifold at the location marked as. Tachyon beams always move downward. Tachyon beams pass freely through empty space. However, if a tachyon beam encounters a splitter, the beam is stopped. So the new tachyon beam continues from the immediate left and from the immediate right of the splitter. Okay, here. Go down and then we start splitting, okay. And then we're at the end, okay. We've been split 21 times. How many times will the beam be split? This example. Start here. Then we can go, I don't think we need a problem anymore either. Okay, we have our lines. We have a tree looking thing. I guess we need to find the position of S and then move downward. Then whenever we have a split, we just have more starting points. And then we move down from those. Then we split. What happens when we split in the same direction? Okay, 2 will create 3. So 4. It's tricky how to count it properly, but I'll figure it out first. Let's do all the splitting. What's it called? Tachyon beam. Let's just find first line. Let's keep these beams locations. So we have the S. We can go point of 0 and S column, 0 row, S column. Then we would go to the next row, right? Beam dot x plus 1 and whatever y is. Well, beam dot y. That's this one. Then you have to check if lines next on x dot, then we're fine. Then fine. Then we have, it's a hat, and we split him. Usually down becomes next, left. So we have to like say list of down. So it stays here, and here we replace it and say happening here? Okay, so every time we have these next, we should add them. So here. Okay, then we have one step. Next row. You can return that list. Hmm. Some point we're done. And then if not, mhm. The last line I'm done. Okay, doing something. The first thing is 1, 7. That's when we go down once, and then we split once. And then we split into 3. I guess. Like sum up the differences or something, right? Hmm. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 16, 20. Okay, so it's about how many distinct splitters I've hit. So I can just keep track of that maybe. Let's do something here. Then I just go and then I can just say splitters.size 21. Okay, let's do puzzle input. This many. And that's part 1 done. With your analysis of the manifold complete, you begin fixing the teleporter. However, as you open the side of the teleporter to replace a broken manifold, you are surprised to discover that it isn't a classical tachyon manifold, it's a quantum tachyon manifold. With a quantum tachyon manifold, only a single tachyon particle is sent through the manifold. The tachyon particle takes both the left and right path of each splitter encountered. Since it is impossible, the manual recommends the many words interpretation of quantum tachyon splitting. Each time a particle reaches a splitter, it's actually time itself which splits. In one timeline, the particle went left and the other one went right. To fix the manifold, you really need to know what you really need to know is the number of timelines active after the single particle completes all of possible journeys. In the above example, there are many timelines. For instance, there's a timeline where the particle always went left, or it alternated, and so on. So there's 40 different timelines. Apply the many worlds interpretation. How many different timelines exist? Okay, a bit tricky. I have to count again differently. You could kind of recursively count, right? Because when it splits here, it's 2 times the oh, but then you have to deduplicate it still. Hmm. Hmm. Well, there's like different ways I can do a combinatorial. Figure out if I know it splits here, then all of the above paths, whenever they split again, they have to consider that again. Always times 2 it. Or, so it's a bit complicated, I think right now. Or I just know already where it splits, so I could make a list of all possible paths. Then I know how many exist. I think that's probably a more straightforward solution. I just need to know the connections. I don't have edge. And B maybe. And then let's do the same. I just keep track of it because it's just one loop. Um, then we go beam. Edge from beam to it. Edges. Now I just have to build paths out of the edges. So I go how do you build paths? Hmm. Is it maybe? Well, it starts with dot A, dot X is 0. Um, and that's kind of like a list. And then the same kind of loop. And then where if next. Actually, it might be easier this time. lines, last index. Let me just go paths. We do next is this, and we do for each path, which is a list of edges. We go take the last edge and B. Then we find all connections. For each next edge, we go then we return that. If everything works out, then we can print paths, not sides. Paths is never used. What? See what happens. Hmm. Oh, so we have one path. Do not find anyone. No, we find two. It's exactly what we want. The result is two paths. Great. Hmm. I think we're only running paths to the end, right? What if I keep all of them? Too many. The path also should go to the end. Just going one too many or something. Oh, now I have everything again. Now I just hmm. Hmm. Yeah, it's still 49,000. Somehow it's going from 14 to 15, 10. Fourteen four. Maybe let's just check the edges. And that doesn't make sense. Why would 14, 14? It should only be connected to these two. So the edges are wrong. Need to go next. They're not next row beginners. Okay, let's see what it says now about the size. 40. Nice. Okay, let's try the real one. Oh, it's working. I actually don't want to filter. So I need to run again. That will take longer because it's 142. Okay, so uh, let this run for a while. And to build the paths, but it just ran super long and was too slow because the data is just too big. And maybe there's some optimization that we can do to build a path like this, but it's not optimal. And I don't know, think about it. And my thought was I can keep track. So I can do it in a combinatorial way. I can keep track how many paths there are. So here there's initially one path. When I go here, there's one path, and then it splits into two. So at that point when it splits, it's one more than before. Then when it splits here again, for each one, there's one more. So here is one, and the second one, and then for here, there's here the third one and the fourth one. And then these ones, because they have two parents, when they split, there's one more path for each of them. So here there's two more, and here there's two more, based on the two coming out of here. So how to easily count that is, while I'm splitting, I can say how much weight or whatever does my current path have. So at the beginning one, and then from here on two, because there's two, and then here it goes into three, because it goes from here once, and from here down twice. So I can just keep track. Then I just count how much weight each of my paths have at the end when I'm done. And then I should get the right amount of things, and it seems to work. So I tried it here. For the small example, what I did is I made a data class that has not just a point but also a weight, x, y, and w. And then the same that I did for part one, I can just add next row w, which is just a list of these points, and I start with 0, the S column, and weight number 1, because at the beginning I just have one path. And then whenever I split, or whenever I go down, I just have the same weight as before. And whenever I split, I just have the same weight as before initially. And then I make this to be a list of results. It's not a set, but a list of these points. And then before I return it after each row, I can just map the points to the weights. And I might have multiple points where I came from two sides to the same point, in which case I just want to keep one entry but add the weights. So I just sum off the values and I map that to weighted points again and return that. That's the idea. And now I'll run it with the big example. We can see that we get minus. And I am still running this. So I just not run this. And there must be some giant numbers in here. Okay. So I just need to change these to, no, just the weight to long and see what that breaks. Nothing. Okay. That's a pretty large number. Didn't think it would be that big. Well, yeah, that's the answer. So part one, we basically just count the splitters, right? So we have 1539. What we do is we just follow the process, go for each row. Either we don't split by just going one down, which is point plus one, or we split, and every time we hit one, we just add it to the list. And then in the end, we know how many we have. And splitting in itself is adding a left and a right while going down, and then adding those all to my list, returning those for the row. Then we can print splitter size. And for part 2, yeah, as I just explained, we go and have weighted points where we start with 1, and then we add all those to a list. And at the end, after we finish processing a row, and before we move on, we reduce the list to only have one item per point and sum all of the weights for those points. So now we know those are the many parents options that we had to get there. At the end, we can just sum all the remaining edges when they hit the floor here. That's it for day 7. Enjoy the rest of your day.